So this is a quick run through of a Open3D Alliance Libre RISC-V talk. Why should we collaborate? Because 3D is hard and it's not the same as high performance computing. We can't rely on NVIDIA, AMD, Imagination Technologies and the company behind Vivant to meet the unusual requirements of non-mass volume products. So working together, flexible standards, everybody wins. It's also a huge amount of work, so if there's no collaboration, each stakeholder team is looking for a 10 to 20 man year development time. With collaboration, not only do we share the time, but also we get to cross-verify each other's contributions and avoid serious and costly mistakes. What is the goal? You get to decide. That's the point of collaboration. So outlined here we've got some ideas and cost and time-saving approaches which are recommended. Key to that is two new platforms in addition to the standard embedded and Unix RISC-V platforms, proposing a 3D embedded platform and a 3D Unix platform. These were quite important. One goal is to have flexible optional extensions so that you can pick and choose. So that includes transcendentals, vectors, matrices, texturization, opcodes, pixel and Z buffers, all is optional. And good software support is absolutely essential, and for various reasons that basically means Vulkan and Vulkan Kronos trademarked compliance. Who are we? Behind the Libre RISC-V SoC are a small team sponsored by Purism and by the NLNet Charitable Foundation. The focus is therefore on efficiency, leapfrogging ahead without requiring huge resources. Basically, we can't do everything, therefore the focus is to ride on the back of whatever technology we can find, software Libre, etc., and to use intelligence, creative intelligence, as a substitute for brute force financial resources. So we looked at the OpenGL API. First of all, Gallium 3D or Vulkan would be better because through that you get OpenGL and OpenCL and many other things for free. Turns out that Gallium 3D is a single threaded interpreter, whereas Vulkan is compiled and you can have multiple parallel resources on the shader engine. Turns out that independent teams provided OpenGL Vulkan adapters. There's also a Gallium 3D to Vulkan adapter in development. So by conforming to the Vulkan API, we get OpenCL compliance for free, Gallium 3D compliance for free, and OpenGL compliance for free. Hooray! Making these kinds of decisions is it's a no-brainer if you want to get it done. So we've taken the same approach for hardware. We're taking an intelligent, creative approach to seek the highest bang per buck for our time and money. So we save on design time, save on implementation time, and our sponsors are happy. So what are the optional things that can be done? Vectorization. It's not essential that a tiny embedded core, soft core, or whatever have vectorization. You can do just as well with software for loops. That is the advantage of a hybrid approach, which is what we're taking here. transcendentals as special opcodes, sine, cos, exponent, log, power, cube roots, etc. etc. These, surprisingly, there's a couple of hardware algorithms. Cordic covers most of those for embedded, and of course for high-end performance you can do dedicated engines. By providing them as optional, you get the flexibility to choose, pick and choose all you would do. Again, texture opcodes, pixels and buffers, everything optional. Pixel conversion YUV to RGB, which is an essential part of the Vulkan API. By the way, it's not linear. The RGB 8888 with floating point 32 to 8888 ARGB is not linear. The floating point conversion to RGB 565 is linear. So that needs if it matters, if the pixel count matters, you want to do it. Optional accuracy. This is for floating point numbers. Embedded, you don't need the full accuracy of IEEE 754, and you don't need full accuracy of Vulkan compliance. These options give implements a huge amount of flexibility. It's not an imposition. If there's anything that is imposed by standards and by other members of the alliance, people are just going to walk away and risk fragmentation. However, collaboration, we are going to need take some hard but easily logically justifiable rules to make sure that in interoperability and everybody saves time and cost. What is essential? Well, the software. If you use anything other than Vulkan, you're looking at a 10 plus man-year effort and going it alone. The whole point of this initiative is collaborating, everybody saves time. Not only that, Vulkan, if you've got end users who you present an alternative API, you're basically condemning them to vendor lock-in yours plus massive software effort. The industry is basically behind Vulkan, therefore it's essential to be compliant with it. So we're looking at two new 3D platforms are also essential. One for embedded, one for Unix-3D. Vulkan compliance has implications for the hardware. With the API being public, interoperability is key, especially given that Kronos compliance is trademarked. Also essential, we need to respect that standards are hard to get right. If you make a mistake in a standard, that's it, it's done. There is no going back. Now, that's not the same as planning in advance for enhanceability, and that also needs careful advanced planning. There must be no ambiguity, no ambiguity where one person could implement one thing and another person could do something else, and end users look at it and go, well, that I don't know what to do now. So it's difficult to get right. Also essential, respecting that for collaboration and interoperability, some things go into a standard that you might not need, but your customers for interoperability purposes definitely do. Examples here, we did an analysis on ISADEV with Mitch Alsop's help, and we came to the conclusion that log plus 1 is an essential opcode to have alongside log, because log plus 1 gives better accuracy under certain circumstances. It's the same hardware underneath, but with additional microcoding, but it's as far as a public API is concerned, if you don't have one, you penalize the other. If you have the other one, you penalize implementers for not having the other one. Therefore, to solve that, you require both. Okay, so that's just have to bear that in mind. It is essential to be mutually respectful and open for fully transparent collaboration. No NDAs, no closed forums. That allows arbitrary experts to come in. Mitchell is retired, he doesn't need money, he's quite happy to help, and his advice is unbelievably valuable. If we have a closed forum, or if we require NDAs, he's just going to walk away. He doesn't need the money. He's retired. He's extremely technically competent, and he will really only be happy with to contribute and to provide us with advice if it is not made inconvenient for him to do so. Why do we need two platforms? Well, if you're going for a hybrid design, it's a unique pragmatic consequences of a hybrid CPU, GPU-VPU. Just a reminder, embedded, you don't even raise any traps, and interoperability is impossible. Software tool train collaboration is incidental. In other words, there is code out there, you use it, you take a snapshot of it, you save money by taking that snapshot, you don't have to release any of the modifications to anything that you're doing, so you save money, and it's the fact that everybody else is collaborating that results in you saving money. Interoperability is absolutely flat out impossible. You're customizing the instructions, you're customizing everything. In the Unix platform, it's the complete opposite. Illegal instruction traps and much more is mandatory. Software interoperability is mandatory and absolutely essential. It's primarily for running Linux-based OSs, but there's also real-time operating systems that are also meeting the Unix platform standard. You make a mistake in your software here, nobody can run your software. You make a mistake in your hardware here, nobody can run your software. That's why the Unix platform exists. The reason for having the 3D embedded is platform as a separate platform is that if you fail to allow implementers to reduce floating point accuracy, it's going to automatically result in failure. There'll be too many gates, do too much power, and that automatically results in end user rejection and customer rejection. 3D Unix, likewise, this is basically down to if you have a pre-existing 3D customers shader engine, which is proprietary, it requires not being compliant with the Chronos specification. It's, well, basically, apart from being a trademark violation, you just punished your customer and they'll walk away. So this is completely different from the Unix specification, where if it's not IEEE 754 compliant, you're hosed there. So you've got these two completely contradictory, mutually exclusive options, and the solution is to allow the software to select the floating point accuracy at runtime. So on the Unix platform, it will be IEEE 754 compliant, or whatever the Unix platform requires, according to the RISC-V specification. But for the 3D Unix specification platform, we require Vulkan accuracy, Vulkan compliance. Simple as that. that stops all the errors. Now, the reason for it being at runtime is because if it's a hybrid GPU, you're going to be running Unix software and 3D software on the same hardware. Okay, now, interestingly, in hardware, you can actually use the same pipelines and recycle the data through the same pipeline hardware, so that you get fast output for 3D and for IEEE 754. Once you put into the more accurate mode, you put the partial results back into the pipeline. It takes a little longer, but you get the IEEE 754 compliance. Now you have a competitive product. What has the Libre RISC-V team done already? Made the decision to go the hybrid route. A reason for this is because if you have in the proprietary world, you have a separate GPU because it's licensed to multiple platforms or is running as a PCI Express external video card. So they have to be instruction ISA independent, and consequently you need to marshal the entire API data into sequential data streams, which are sent over from user space memory over to GPU memory, and then unpacked again at the other end, and finally make the function call on the GPU to process it there. Then when it's done, you do the reverse again, you get the response and you marshal that and everything. This is complete insanity. The cost of that, in some cases, you end up actually putting a full-blown RPC mechanism into the kernel, into kernel space, which is basically insane and costly. So we decided not to do that, and by doing a hybrid GPU route, you basically, the Vulkan calls are done in RISC-V opcodes with which has huge cost savings and benefits, etc. Plus developers, it's easier because they can single step into the actual 3D space rather than having to have a separate debug engine running on the GPU. We also developed SimpleV, which is a parallelizing API. It's very difficult to describe because there simply does not exist anything like it. So there's not even any common computer science terminology that we can refer to. Ask me, contact me and ask. I'll do a little bit of explaining later on in a couple of other slides, but yeah. We also started on Kazan, which is a Vulkan SPIR-V to LLVM compiler. It is not an interpreter. It takes SPIR-V and actually compiles SPIR-V opcodes into LLVM intermediate representation opcodes, and then hands that over to an LLVM just-in-time compiler, and the result is we don't have to write a full-blown compiler. Hooray! We also started work on a highly flexible IEEE 754 FPU, which obviously we will add a Vulkan accuracy to as well. It can do dynamic SIMD partitioning. We're currently working on a multiplier which is partitionable. It's currently a Wallace multiplier. We're going to be modifying it to a Dada 1. It's complicated, and it's also Libre licensed. We started work on a precise CDC 6600 augmented out-of-order engine, which is multi-issue capable, contains predication. It's a variable issue at the front end. This is only possible thanks to Mitch Alsop's help. Mitch is the designer of the Motorola 6800, the 2019aug29, excuse me. He's also responsible for the highly efficient Opteron series, which was pooping all over Intel back in the late 1990s and early 2000s. This is all being done transparently, publicly and transparently, and it's all Libre licensed. This is to respect our sponsors' mandate for the NLNet Foundation under their Privacy and Enhanced Trust program. It's also just plain common sense. If you develop things publicly and transparently, random people can offer their assistance and join in, and you avoid making costly mistakes. Why would we develop SimpleV and why not use the vector RISC-V vector extension? Well, there's several undiplomatic answers which I won't go into. The practical ones are that it is RVV is designed exclusively for supercomputing. It has not been designed with 3D in mind. Its primary contributors are people from Northrop Grumman, etc. People with a huge amount of experience in supercomputer and high performance vectorization. With the RISC-V Foundation operating as a closed membership thing, we simply can't contribute. We can't have a say, an independent say, in what goes into RVV. Now, ironically, RVV was developed as a alternative to SIMD. SIMD is an order n to the 6, yes, really n to the 6 opcode proliferation on the instruction set architecture. You have massive opcode proliferation. It's not uncommon for a SIMD processor to have thousands, literally 3, 4, 5,000 opcodes. You only have to look at the Intel AVX 512. They're up to like 128-bit opcodes, for goodness sake. So it's pretty mad. So ironically, the same principle that caused RVV to be created, the SIMD considered harmful article, the same logic applies to RVV. So I don't know if you're aware, but 98% of the scalar floating point opcodes are duplicated in RVV, and in addition, a large portion of bit manipulation opcodes are duplicated as special opcodes for use in predicate masking. So 3D has some very specific and special requirements. Swizzling, for example, that just do not fit. You're running out of space. You're running out of opcodes, bits. A swizzle needs a minimum of 12 bits if you do it in one way, but if you do it it's a bit of I won't go into the details, but we can't extend a 32-bit. There's not enough space in the 32-bit opcode bank, so we have to go to 48-bit or 64-bit, which means that you inherently are penalized by instruction cache power consumption. So what we decided to do was, in SimpleV, is you prefix scalar opcodes, all of them, all scalar opcodes, with the exception of things like jump and link, JLRR, and things that modify modify the program counter, obviously. Well, one person did actually suggest that we do use simple V on a program counter to start multiple threads, multiple hardware threads, which is a great idea but scary as hell. So not going to do that. Not as a mandatory option anyway. So when you say scalar, prefix scalar opcodes, I mean all of them. That's RVC included. So not just the current RISC-V standard opcodes, but future opcodes as well, and custom opcodes and 3D scalar opcodes are all prefixed with context to create vector equivalency. So what that means is that the entire IVV major opcode becomes free for use as a 3D opcodes. So simple V prefixing. This is basically taking the 32-bit opcodes and the 16-bit opcodes and prefixing them with predication and a vector tag. So there's three prefix types which are designed. SVP32, which is prefixed RVC. There's P48, where you take 32-bit opcode and embed it into a 48-bit RISC-V opcode format, and then there's an additional one, which is P64, which is the 32-bit opcode, unmodified scalar opcode with the same prefix as used in P32 and P48, and then extended further. It's just about possible to fit P32, the prefix RVC, into the three of the custom op32 opcodes. It's extremely jammy that's even possible. As explained, P48 takes standard op32 scalar opcodes and prefix them with the same 10 bits as is done with the RVC prefix, and then additional vector context on top of P48. Prefixing is basically a bit like SIMD. You can specify in the prefix as a single instruction, you can specify that the length is to be between 2 to 4. You can also specify that elements are to be packed into the standard floating point or integer register file, which has the implication that the opcode element widths can be overridden in the prefix. So you can specify that you want this scalar operation, which would ordinarily be 64-bit, you want it to be a 16-bit instruction packed into the 64-bit data for 16-bit operations done all at once. So when I say it's a bit like SIMD, it's not. It's similar to RVV's sub-vector system. However, you contact me for details. There's much more to it. So, as far as compilers are concerned, simple V prefixing is very convenient, but it's not very space efficient, because every single opcode has a 16-bit prefix, or even with RVC. Using RVC, you can't use full things, but it's still 32-bit. So basically, that's what the vector block, VBLOCK, is for. What is a VBLOCK? Again, unfortunately, it's very hard to describe because there's nobody has done anything like it. So there is no computer science terminology. There's a few things. It's a bit like register tagging, which was commonly done in the 90s. Texas Instruments used it in particular, and also the mill the mill architecture uses tagging, but they do it in a quite a different way. So it's a bit like VLIW, only not really, because those instructions have a sequential context that must appear to be in sequential order, just like in scale operation, whereas VLIW, it's a simultaneous thing. So you have a block of instructions which are prefixed with tags, which give you extra context, to the scalar instructions within the context or the length of the block. Those sub-blocks include specifying the vector length, the maximum vector length, which is similar and identical to the RV vector system. There is a swizzling block. There are vector and width, element width overrides, and there is also predication. And this is all added to scalar opcodes. There are no vector opcodes, and you do not need any. So the basic rule is this. In the context, it goes, if you use a register in a scalar opcode, and the register is listed in the context, simple V mode for that instruction is activated. And activation results in a hardware level for loop issuing multiple contiguous scalar operations, not just one instruction, multiple instructions. And that means that the program counter is paused, and you go into the a sub program counter loop. So consequently, implementers are free to implement that loop in any fashion they see fit, just as you are free to implement program counter incrementing by having multi-issue or single issue or out of order. You are entirely free to do the same here for these subcontexts. You can do SIMD as long as you have predication on it. You can do multi-issue. You can do single execution. You can pause the program counter. So for an embedded system, it's extremely flexible. Right? There is no penalty for if you want to, you can also use traps to implement the loop, as long as there is a minimum requirement. It'll be very, very slow, but it will be require some firmware to implement the emulation, but it is an option. So what other standard proposal will we put in? Z transcendental and some trigonometric opcodes. These are all optional within each group, so that embedded implementers have some leeway in what they choose to do, not just in the software but also in the hardware. We also have something called an ISO-MUX, an ISO namespace proposal. This is absolutely essential. It stops arguments over the opcode, 32-bit opcode space. And basically what it does is it allows you to page in at runtime, cleanly page in new opcodes without fighting over the space. It also has some other benefits, which is that if there are any emergency changes needed to the standards, the ISO instruction set, they can be done in a managed way, which provides backwards and forwards compatibility without there being drastic damaging decisions to the community and to the RISC-V reputation. We're also proposing a move swizzle and a move X. Now, mover X is basically you look up the register contents and you use that to look up the register contents, and then you put the result into things. So it's basically registers brackets. Registers brackets are destination equals registers brackets the source. Move is missing from RISC-V. It's done as a pseudocode alias, which is actually add register 1 to register 2 plus 0, or you could use or whatever you'd like. But apologies, my daughter singing wonderfully. MoveX does not exist, so we have to make one. So move instruction does not exist, so we have to make one. So that also provides us an opportunity to do a move.swizzle instruction. There's really not enough space unless you go to a 64-bit special opcode to specify the source, destination 1, destination 2, destination 3. That requires 32 bits to do that in a single instruction. That's just a swizzle. I think swizzling is basically you can select in a vector, you can select the source and destination, you can swizzle, permute the elements of the vector thing. So what we propose is move.swizzle, which just allows you to do a thing. And of course you can then what's the word? Macro fuse several of those together to produce the effect of a multi-swizzling source and swizzling on destination on the cell thing. You get the idea. Additional thing, dynamic floating point accuracy. This is needed for fast Vulkan native selection of some opcodes, but also to switch between fast 3D accuracy, Vulkan compliance, and IEEE 754 at runtime. There's a huge amount more to do. We need your input and collaborations. 3D is basically really hard. Now, all of these standards, the key strategic premise is that they are required to be public standards. Why? Because the software is supposed to be public. Why is the software public? Because it has to be Vulkan compliant. And if it's not Vulkan compliant, you're not going to get end user adoption. Customers will already have their own SPIR-V shaders. They're not going to redesign the entire game or the entire 3D application just because you've invented a new 3D standard. It's just not going to happen. So, unfortunately, this is not well understood or accepted by the RISC-V Foundation. We fall between the gap of the Unix platform, which is designed for collaboration and cooperation and interoperability, and the embedded status, where it is expected that in RISC-V, if you step outside of what is mandated by the RISC Foundation, you're into what's called custom territory. Custom territory is not appropriate. Custom status is not appropriate for a high-profile, mass volume, end-user API compliance and interoperability, such as Vulkan. If we were doing a proprietary GPU which had no intention of meeting the user interoperability and user programmability, custom status would be appropriate. It is this combination of being hybrid CPU and GPU that makes public collaboration and standards compliance, absolutely, official standards recognition, absolutely essential. So, summary here, 3D is hard, and vectorization, if you do a pure vector engine, you end up with a commercially rejected solution. The reason, as Jeff Bush's Nayuzi research showed, if you do a software rendering only engine, you get 25% of the power performance level. Your gates, basically, you need to put down 4 times as many gates, and your customers are penalized by 4 times the amount of power consumption as commercially acceptable offerings at this time. So we need these custom Oxford codes and the flexibility that's associated with it, and the associated standards interoperability. It's sensible to go with layered optional extensions, so that I think this is going to be key to acceptance by a wide variety of the 3D Alliance members. We want people to feel comfortable that they can do a low power soft core and still benefit from the collaboration with members who are doing embedded 3D GPUs or AI, putting down 4096 cores with 64-bit 64-way vectorization done in a single cycle. There's no reason why we shouldn't collaborate, but it's just, it means we've got to be open and transparent about it. With the custom specialized Vulkan SPIR-V Vulkan compiler being an absolutely essential, critical, strategic requirement for end-user customer acceptance, the RISC-V vectorization effort is of marginal value. If aside from anything, we have to develop the SPIR-V Vulkan compiler anyway. It's a SPIR-V to LLVM intermediate representation compiler. RVV doesn't really, it doesn't feature in that. Plus, it's still under development. The compiler doesn't exist, and it's just, if we make it a critical hard dependence, I mean, you could make it optional. It's fine, but with you get the general idea. Now, it's important that you question everything. One group, one stakeholder cannot dictate this process, and cannot be the sole exclusive contributor, with everybody else sort of going, oh no, I don't like that. So it's your input, willingness to take active responsibility for tasks that your company or organization is critically dependent on. This is extremely important. Public and transparent collaboration is key. There's just too much to do, and we need to collaborate and be open about it, and allow random, arbitrary people such as Mitch Alsop and other people with huge amounts of expertise to be able to come in and offer advice. So, yeah, thank you very much. Some links for you. Any questions, I can be reached on the mailing list. Thank you very much.